Bonjour à tous et merci de nous rejoindre pour ce webinaire H2O Lyon. Alors, en guise d'introduction, pour nous laisser encore un peu le temps, juste pour vous rappeler que H2O Lyon, donc c'est une école universitaire de recherche basée à Lyon, qui regroupe les chercheurs lyonnais, mais aussi doctorants et étudiants tous travaillant sur l'eau avec des disciplines différentes, et que elle se repose sur trois piliers qui sont fondamentaux pour ces actions, qui sont le lien entre les formations et le monde de la recherche, le lien aussi avec les praticiens, l'interdisciplinarité et l'ouverture internationale. Et c'est dans ce cadre de l'ouverture internationale que chaque année, H2O Lyon a le plaisir de soutenir des mobilités de chercheurs internationaux. Donc cette année, c'est Santiago YEPEZ qui nous a rejoint pour travailler sur Lyon. Donc il sera parmi nous jusqu'en juillet, si c'est bien ça. Si Santiago, sinon t'hésites pas à me corriger. Donc voilà, donc si à la suite de ce webinaire, vous avez envie de le contacter pour pouvoir échanger avec lui, n'hésitez pas, il est encore là avec nous quelques temps. Et du coup, je vais laisser la parole à Clément qui va nous faire une courte introduction sur le webinaire.
Merci Bastien. Donc effectivement, donc dans le cadre de ce webinaire H2O, qui porte sur les travaux de Santiago YEPEZ, notamment sur la signature spectrale au territoire et ses applications, je me permets de faire une courte description de la carrière de Santiago YEPEZ. Donc il est professeur, géologue et chercheur associé à l'Université de Concepcion au Chili, avec près de 25 ans d'expérience dans l'enseignement universitaire et la recherche scientifique. Son parcours universitaire, il comprend un doctorat en hydrosédimentologie et détection par satellite, obtenu à Toulouse, dans l'université Paul Sabatier, il me semble. Et il a également effectué donc, des études postdoctorales soutenues par le Collège de France et l'IRD. Concernant les thématiques de Santiago Yepes, donc ses recherches apportent principalement sur l'hydrologie, la géomorphologie fluviale et la télédétection hyperspectrale jusqu'à la qualité de l'eau, et donc notamment avec une forte expérience de terrain et de recherche sur des réseaux fluviaux au Venezuela, en Colombie, au Brésil, au Chili, donc en Amérique latine, et également en République du Congo, et donc en collaboration avec des universités et des centres scientifiques internationaux. Et aujourd'hui, donc, il occupe le poste de coordinateur régional du programme Water pour l'Amérique latine et les Caraïbes, donc ALC, dans le cadre du programme hydrologique intergouvernemental FI de l'UNESCO. Et donc, ça permet de contribuer à la coopération scientifique internationale et la gestion durable des ressources en eau.
I would like to say thank you to the H2O program for the invitation to this webinar. Today, I would like to talk about the imaging spectroscopy obtained from different hyperspectral sensors and cameras. And I'm going to show how this data can be transformed into important environmental information that supports monitoring, management, and also decision making. I'm going to talk about different applications that we developed in the last few years relate to the transport sediment in large river like Orinoco Basin, and also I'm going to talk about the study of the eutrophication process uh, in a very important lake in Chile is Villarrica Lake. We are going to use some indicators, some geophysical indicator to establish the trophic state in this lake, combine hyperspectral profile, and also combine in situ data in order to create retrieval spectral model to create synoptic map to understand the variability of this indicator. And also we're going to use a new application using a new hyperspectral cameras, HiSpec. It's a new kind of hyperspectral camera that is a high resolution, not only not only relate to the spatial resolution, the signal noise ratio of this kind of camera is very important to separate, to discriminate, to apply the discrimination of different tree species. And we are going to show this new project that we use only the signal reflectant from this camera in order to characterize different tree species. And the last application will be related to the
Par rapport aux convocations, aux oraux de L3 que j'avais à faire passer, je crois que c'est Alexia qui a dû s'en occuper.
I'm going to use the preliminary studies of relate to the aquatic vegetation in a experimental study at laboratory. We evaluate the different conditions of light in control and in natural conditions. We evaluate the attenuation of the light in different species of aquatic vegetation. And it's very important for the implication in remote sensing in order to classify these species along the Rhone River. Okay. Well, here we can see three different spectral signatures representing water, vegetation, and sediments. We can see the spectral profile from the water is very specific. The attenuation of the light is very strong. We have a big absorption along all the electromagnetic spectrum. Only 50% of the radiance to leave from the water is important to analyze the spectral profile related to the water. Also, we have the spectral profile from the vegetation. The interaction between the red region and the near infrared is very important is related to the chlorophyll A and also the leaf structure of the vegetation. And also we have different absorptions related to the sediment. Here the idea is or the important message is that this spectral difference can be transformed into environmental information that we can map and also monitoring, okay? In the next example that I'm going to present in each case study, I'm going to pass from study the sediment transport, the water quality, the forest composition, and also the interaction of the light with the attenuation of the electromagnetic spectrum that coming over the surface water. This slide illustrates the link between the spectral measurement and environmental decision making. All start with the acquisition of the spectral profile in field and laboratory or using airborne cameras. And the idea is try to use this reflectance signal in order to extract information like indices, spectral indices, some a specific indicator related to the absorption and reflectance from the interaction of the light. And then we combine this information, this indicator, with some biophysical variables. For example, in the case of river, we use the concentration of suspended sediment. In the water quality, we use turbidity or chlorophyll A has indication of the trophic state in the lake. And also in the case of the evaluation of the classification of the tree species in large forests like Encore Park, this is the study area for this application. We collect the reflectant from the canopy of each species, and the idea is try to use the difference of the spectral profile in order to classify different materials. Okay. combine this data, we can create the retrieval model, and then we can convert, we can pass the pixel to ecosystem. We can obtain this distribution map, this synoptic map, and we can use this information in order to monitoring, assessment, planning, or implement conservation programs. I'm going to show in this application, as I told you before, I'm going to implement application in Orinoco River to study the sediment transport, studying the variability of the spectral profile at different stages of the hydrological cycle. I'm going to use the chlorophyll A and turbidity to evaluate the state trophic inlet. I'm going to use also the spectral profile from different camera high speed in order to understand the canopy reflectance and try to classify the forest species with high detail. And then we are going to show some application in aquatic vegetation, try to understand the attenuation of the light and the whole water column. Changing, for example, variables has depth and turbidity. Well, in the first case study is we are going to focus in the main hydrological station in Ciudad Bolívar. We are going to study the how can estimate the suspended sediment concentration by remote sensing. The idea is try to establish this correlation between in situ data. We collect some water samples. At the same time, the path of the satellite is in the study area. The idea is try to establish which band is more sensitive to the correlation with the variability of suspended sediment concentration. When we evaluate this, we create the retrieval model, and then we pass a second objective is try to provide insights into the spatial distribution. We create this synoptic map in order to understand what happened with the mix of the suspended sediment, detecting which areas are more important for the deposition of sediment. And this is very important because in this part of the river, there is important to keep the navigability. Every year, there is an important cost of the dragage project to keep the navigability in this part of the river. The result of this work provide a solid base for exploring alternative methods to estimate sediment concentration in large rivers. And well, the study areas is the watershed of the Orinoco River. There is a specific asymmetry between the left band and the right band. We can see by colorimetry the color of the lens band is related to the erosion of sediment that coming from the Andes, and the other side we have the influx that coming from the Guyana Shield with characterized for poor in nutrients. The asymmetry is between both band are very important, and we take advantage of this different in order to create the evaluation of the spectral signal from reflectance to characterize the concentration of suspended sediment. But in this slide, we show the acquisition of the in situ data at different sections of the river. The idea is to implement the acquisition from radiometry using similar equipment that used at the ONS. It's an analytical spectral device, field spec4. And the idea is try to collect a signature spectral with collect at the same time water samples and apply the filtration to estimate suspended sediment concentration. The idea is try to use this cellulose filter, and we wait before and after the filtration process, and we establish the suspended sediment concentration and regard the volume of the water sample. Well, in this slide, I show you an aspect very important is the acquisition of the spectral profile on the water surface. It's necessary to avoid the effect of sungling. We need to collect the spectral profile at different sequence using different angles. For example, we use the radiance downwelling and onwelling at a specific angle in order to mitigate the effect of the specular reflectance. And also we use a specific spectral, is like a placard in order to obtain the irradiance and downwelling. Using the formula from Motley in 1999, we combine the information from different acquisition in order to mitigate the effect of the sungling. That permit to increase the correlation between the different components in the water column with the signal from reflectors. But also, we need to apply this correction also in the time series of the satellite image. In the case of Landsat, at this state, we test different methods of atmospheric correction. We use the flash. Landsat A super reflectance is a new project from the USGS, and also standard method from atmospheric correction like dark order subtraction. We evaluate this atmospheric correction using the signal from the spectral profile. If you see the black line in the graphic, this corresponds to the real behavior of the reflectance. And the other lines, green, red, and blue, are related at the different methods of atmospheric correction. You can see the red it corresponds to the product from the USGA, and you can see the reflectance are very similar between the reflectance from the spectral profile at the surface water. We try to collect information at different states from the hydrological state in order to estimate it, to see also which spectral bars are more sensitive to detect the variation of these indicators. For example, in this part of the river relate to the granulometry and the grain size, the red bands and near band are more sensitive to see this change. Also, it's very important to use a sub-product that coming from this atmospheric correction method that is Cloud QA peak. Is a raster that you can obtain the concentration of aerosol, the occurrence, for example, the shadow, clouds, and you can use this kind of product to create a water mass in order to avoid some noise that can affect the correlation between reflectance and the biophysical indicator. But to understand or to try to apply this kind of methodology using satellite images, as you know, when you acquire information from satellite images, you only obtain information from the surface. But in the case of the Orinoco River, it's very important to know what happened in the water column. For this reason, it's necessary to select a good section in the river to promote the homogenization of sediment. For this reason, we select the section of Ciudad Bolivar. We have a kind of funnel effect in this part of the river, and that promotes some turbulence, some geomorphic threshold that promotes this remotion of the sediment. We use uh, uh, acquisition of acoustic backcasted Doppler acquisition from ADCP transit in order to collect vertical measures of suspended sediment concentration. If we try to compare the average of the all in situ data with the average of the all surface suspended sediment. This was repeated at different stages of the hydrological cycle in order to understand if this part of the section is dominated by this homogenization of sediment. But we can see the river is affected by the hysteresis process. It means there is no relationship between the discharge and suspended sediment concentration. We have in French is barrage hydrologic. I don't know in English. I think it's dam hydrologic. When you have the high water in the main flow, when the tributaries coming to the main channel, they are stopped by the current. But when the water level descends, this water is liberated, and you have the second peak sedimentary in this stage of the river. For this reason, we don't have a correlation between the suspended sediment concentration and discharge. But it's important to know the context in order to apply the remote sensing, because when you acquire information, you only obtain the information from the surface. But we apply also different statistic validation, for example, the bootstrapping approach, in order to evaluate the error of the correlation. We use estimation error, mean absolute percentage of error mapped. We can see sometimes when we have low values of suspended sediment concentration, sometimes the signal of reflectant, because the value of the concentration is very low, the relationship is lost. But it's normal in this kind of application. Using this information, we can create this time series of suspended sediment concentration. Is an advantage to be capable to estimate the suspended sediment concentration in a long time series. For example, in this graphic, you can see the black balls are associated with the Earth survey suspended sediment concentration. And using the retrieval model, we can recover all these measures along the time series with a great precision. Well, using this information, then we can convert the pixel from each satellite image into the asymptotic map. And that's very important because this shows the spatial distribution of suspended sediment along the river. The results show clear transport patterns with sediment mixing, often starting near the river banks and moving toward the channel center. And we can identify the specific site where the deposition is more strong. that is very important for the dragage project, and sometimes are no, they don't have idea what happened in the bedlock of the river. You can see in the slide the relationship between the different photos with different conditions. And also in this cartography, you can see the variation of suspended sediment concentration at different stages of the hydrological cycle. Well, now I'm going to talk about the case study 2 related to the evaluation of the water quality in the Lake Villarrica. The idea is try to answer. We recently published a new article that is called Evaluation of Baseline Water Quality Condition and Episodic Biomass Increase in Lake Villarrica using hyperspectral and multispectral data. The idea is try to answer if we can evaluate the eutrophication process in lake using satellite images. And we select the Lake Villarrica is a very important lake for the tourists, for the recreational activities. But in the last year, it's affecting also for the urbanization, expansion of the urbanization that affecting the shoreline specifically in the near to the Pucón town. The idea is try to evaluate the whole water body, but we collect a lot of information in this part of the lake because we have the influx from the Pucón River that is affecting by agriculture activity, livestock farming that increase the nutrients related to nitrogen or phosphorus that produce sometimes with the conditions the climate variability are very specific that promote the algae bloom in some part of the lake. You can see this effect in this next slide. The trophic state of this lake is mesotrophic. I mean the values every year, every month is very low, but has I told you before, sometimes some periods of summer season we have this episodic of increase of biomass in the lake. Well. You can see also this using the historical data set from chlorophyll A, sorry. We have almost 40 years of continuous data set. And we can see in the graphic B, the values are very low, but sometimes in a specific episode of summer season, we have this increase of algae blooms. The idea is try to evaluate the trophic state to monitoring frequently this lake in order to mitigate the impact of the nutrient that coming from the Pucón River. You can see also the climograph to see which months are more important to evaluate. For example, the summer season is December, January, February, March. Are related to this increase of biomass episode in the lake. I know we collect water sample, but at the same time we collect spectral profile from hyperspectral emitters. The different curve, the different spectral profile correspond to different chlorophyll concentration. By comparing both datasets, we found that the blue, green, and red wavelength are the most sensitive to the chlorophyll A changes. this wavelength became the foundational uh, base for the base for create the retrieval model to evaluate this condition. In the next slide, we can see this graphic. We compare the concentration of chlorophyll A from each measurement in order to determine the coefficient of determination. We can see the wavelength more sensitive to the variation of chlorophyll A is related to the visible region. And then we have a lot of low values in the coefficient. That for this reason, this is a cross validation to determine which kind of spectral index is necessary to implement to evaluate the variations chlorophyll A. In this case, for the data from Landsat 8, 9, and Sentinel-2, we use the spectral index, for example, that use the blue and red band, and also the green and blue. That was the best option to apply the estimation in this lake. Sometimes we are not trying to improve the with new models for this spectral inversion. In this case, we are more interested to apply traditional coefficients, for example, traditional indicators like uh, ratios or single bands spectral in order to estimate the variation of chlorophyll A in the lake. Now it's possible to use other kind of estimation. For example, empirical models that use machine learning. The learning is possible, but sometimes it's very difficult to understand how recover the time series from these indicator. But in the next slide, you can see we use the best spectral index. We develop chlorophyll retrieval model for Landsat and also for Sentinel-2. Both models show a good performance, explain about 75% and 80% of the Earth survey variability. You can see in the retrieval model from the Landsat is very characteristic because we collect information from samples in a specific periods we had algae blooms, but was not possible from Sentinel-2. When we combine these data, we try to synchronize the collect of the water sample with the path of the satellite. In this case, only we was able to acquire information from high values of chlorophyll using Landsat A. My idea is not try to say Landsat is better than Sentinel. For me, is very similar. The idea is try to say maybe in the future it's necessary to synchronize the acquisition of water samples with the path of the satellite in order to have a better, a robust retrieval model. But using all this method, once the model were ready, we transfer the satellite image into chlorophyll maps. What we see is a gradual increase in chlorophyll over time, particularly near the shoreline and close to river inflow. This is a real power of the remote sensing, moving from the few field measure to a complete picture, a synoptic picture of the water quality across the entire lake. Well, this is another slide that show the Sentinel-2 also confirms the patterns or surveyed with Landsat. The lake is generally in a good condition, but recent years show increase. For example, in this part of the lake is related to the season summer. Sometimes we have the increase of the biomass. It's very important to continue the monitoring. My reflection from this research is not try to say we always need to use the satellite image combined with in situ data to estimate the suspended to estimate the indicators like chlorophyll A. The idea is not say the traditional monitoring, the standard monitoring punctual to collect samples is very important, but I try to spread it's important combine this kind of traditional monitoring system with a new technology using this kind of synoptic map to try to understand the process that happened in the whole in the entire lake in the system. Okay, and moving to the next test, we try to combine this analysis with alt, satellite altimetry, for example, from the new satellite SWOT, in order to estimate the water level. Also, if we have the bathymetry, we can establish relationship between water level and volume. And that is very important to understand what happened with this eutrophication process. Also, the idea is try to implement new technology using hyperspectral camera. For example, we collect information in a new lake in Laguna Grande. The idea is try not only identify the variation of chlorophyll, like the idea is try to determine what kind of pigment is related a specific cyanobacteria. Sometimes this kind of cyanobacteria is harmful for the health from the people that use the lake for recreational activities. Okay. Well, we move now to the third case study using hyperspectral imaging to classify native tree species. We use study area the Encore Park. The Encore Park contains one of the most diverse native forests in Chile. Sometimes the species has very similar canopy structure. That is very difficult to classify using multispectral data because the multispectral data has specific probe bands. It's not enough to separate different spectral signature from each species. But we collect the information from each line of the hyperspectral data. If you see the line gray, is the trajectory that follow the pilot. It's not crazy. It's the strategy to collect information with the same geometry of the sun, because this is very important to keep the same specific geometry to guarantee the radiometry when we create the mosaic for classify this species. When you can see the airplane and also the new cameras high speed with the IMU, the inertial measure unit, to see the variation of the geometry when we acquire the information with this camera. And the idea is it's very important to give the message that I think there's 50% of the analysis using hyperspectral image. I think 50%, the most important is the preprocessing. This is related to the bird side. calibration, it's related to the geometric calibration, it's related to the atmospheric correction, and also sometimes when we working with vegetation, the effect of the reflectance and the bidirectional reflectance, the phenomenon is called BR, BRDF is affecting because sometimes the leaf of the vegetation has a typical geometry, but when the leaf change, you have a variation in the signal from reflectance. You need to normalize this kind of signal before to start the classification using machine learning, deep learning. I think the most important process is, or the most important step is the preprocessing of the image. But we collect the different in situ data. I don't know nothing about the species of the tree or the tree species, but I use a specialist that can identify the species in situ, and we collect with a specific map the, the canopy using the canopy height model to select the position precise to create the data set to training the model for the classification. Well, here we evaluate 5 different ways of processing the spectral data and 5 machine learning algorithms and deep learning. This is very important because the idea with this research is sometimes it is similar important to apply different spectral separability methods that select the specific machine learning method to classify the species. For example, in this case, we combine reflectance normal, minimum noise fraction is a TILE's component principle, the spectral binary, every 3 nanometers, principal component analysis, standard normal variate, applied with Savinsky-Golay smoothing or mean centering. There are different methods to try to improve the separability spectral from different materials. And then we combine every method with different machine learning classification. We can see in the comparison from the different spectral separability methods, the MNF, the minimum noise fraction, was the best performance. And you can see with the combination, for example, the classification using no parametric methods like supervector machine, random forest, and also common calbus or XGBooks or deep learning like multi-layer perceptron. The combination of supervector machine and minimum noise fraction was the best performance. That indicate that maybe it's important the selection of the good separability method has the select the best method for the classification of the image. Well, we use the in situ data. We separate 70% for training the model and 30% for validate statistic, and we create a confusion matrix. The confusion matrix tells us which species the model can truly distinguish. The darker the diagonal, the better show the better classification. What is remarkable is 14 of the 18 species achieved accuracies above 80%. In some species, reach values close to 98 and 99%. That is very good result. We have a few misclassification, for example, concentrate among species with very similar spectral behavior, but this is normal. maybe also is because the quantity of the in situ data is not balanced. It maybe can be a problem when we try to classify um, this, the species that has similar reflectance in the canopy. Okay. Well, we use this information to create this synoptic map. After training and validate the model, we generate the species distribution map for the entire forest. And this is where remote sensing becomes especially powerful. Instead of knowing the species composition, uh, uh, we can visualize how the species are distributed across the whole landscape. That has implication for ecology application, for understand the biodiversity of these kind of species in this complex uh, temporary forest raining in Chile. Uh, and I think the real shift is not the classification inside, but the ability to transform spectral signatures into a composite map of biodiversity at the regional level. Well, I'm going to show, I don't know if I have, when you can see the distribution of different, the dominance of different species in the park on core. And I would like to show quickly another application in another part. The name is Caramavida. Is related to a specific species from related to the Araucaria araucana. It's a 1,000-year-old tree. In recent years, has begun to show signs of disease caused by pathogens, or maybe for the exacerbation of this pathogen by the climate change. And what is exciting is that this approach is not limited to one core part. We can use this mosaic in other regions. We can see this type of species is affected by this disease related to the pathogens like Phytophthora cinnamomi or other agents like that affecting the health of the species. Now imagine you have the vast areas from the forest. How to identify the species of Araucaria araucana is very easy because the geometry of the canopy is particularly is the verticillus. I don't know how to say the verticillus is very characteristic in this kind of vegetation. And using only a component principle, you can see, for example, if you give a specific color, for example, green, you can detect all the population from Araucaria araucana. You know also this, you can evaluate the condition of these individuals of Araucaria. Using the extraction of the spectral profile, you can evaluate the difference in the spectral signatures associated with growth stage or physiological condition or drought stress or pathogen infection that is easy to use in this kind of data. Well, finally, I going to show the last case study related to the spectral behaviors of macrophyte and algae across controlled and ambient light water columns. The idea is try to understand the implication to use after this the spectral libraries to use to classify the macrophytes submerged and emerged in the Rhone River. Well, our last example was focused on aquatic aquatic and classification of the forest, but now we're focused in a different challenger because the forest is more easy to determine the species because you don't have the problem with the water column. In this kind of environment, the attenuation of the light is very strong. And for this reason, we start to develop a new resource, experimental analysis, using a hyperspectral radiometer, an analytic spectral device, fields per 4 also. And we try to answer this question. What are the limits of hyperspectral discrimination of aquatic macrophyte across different conditions of depth and turbidity? And then we try to use this project, follow a simple idea, start and small and scale up to begin with a acquisition from the individual plants or aquatic plants in order to create a spectral library. But not only create a spectral library at the surface, the idea is try to understand what happened with the macrophytes at different conditions of depth or different conditions of turbidity. As you know, the water column in the Rhone River is very turbid. That affecting the reflectance signal when we try to use classification using, for example, multispectral satellite image. But using this, we can create a specific spectral library, and we can use also algorithms for classification. And then we try to move to use another sensor, maybe hyperspectral cameras, airborne, or another kind of drone, multispectral, to evaluate the application using this spectral library. But this result is very preliminary. We start to evaluate different species of macrophyte aquatic. We collect this information in the laboratory LEGNA, and the idea is try to use this cylinder to evaluate different conditions of depth. But that was the first stage of the experimentation. The problem what we have in this first attempt to evaluate the attenuation of the light was the cylinder is transparent, and the reflection of the light affecting the wall of the cylinder. We need to cover with a material black in order to mitigate the effect of the light, artificial light. But we can see here in the first spectral library, we can see the difference between different species. Also, we can see in the shower infrared the difference relate to the water vapor. Water vapor, because sometimes the humidity of different species are more strong. And you can use this information also to separate the material. Well, the idea is try also combine this information of the spectral libraries with combine this in the future with a new product from Sentinel-2 that is coming, Sentinel-2 Deep Resolution 3. This is by deep learning, we convert the pixel from 10 meter to 1 meter. The idea is try to understand the dynamic of the aquatic vegetation. But it's very important to be careful because this new product is created by deep learning, sometimes create artificial picture. It's very important to combine this with another source of satellite image, for example, Pleiades Neo, will be very good to understand. But we can take advantage of this time series to evaluate the dynamic with a great precision. But we start to implement this analysis in the next month. Okay, but we can see another spectral library. I'm going to go more faster. This is the graphic that shows the heart of the study. We start with a very distinct spectral signature, but as the plant were placed deeper in the water column, the signal uh, rapidly witnessed the first region to disappear in the near infrared, which is normally one of the most informative parts of the vegetation spectrum. And we use this kind of spectral profile also to apply the the first derivative and the second derivative in order to obtain the specific peak of the wavelength that that is very important then to use to classify using cluster method to try to difference to separate different material. In this stage, we start this study and at the month of February, it was not possible to go to the river. The idea with this new spectral library was to simulate the spectral band from each sensor. For example, Landsat A, Sentinel-2. We use the, the spectral responsivity from each band, from each sensor in order to convert the spectral library from the hyperspectral radiometer to the spectral library from each band. We apply a convolution and integration from the width of each band in order to be precise. And the idea after that is how we know where is the different species, for example, Potamogeton, Shara, or Vallisneria. The idea is try to simulate these species in different captors and apply, for example, component principle in order to see in different stage or condition of heat or turbidity to see how is the mix of different species. For example, in the first level of the deep, we can separate very good the species, but when we have a deep near to 45 centimeter, you start to see how the species start to mixing. That's very important for the implication of remote sensing when you try to classify using sensors at the level of the river. Well, finally, I going to we pass to examine river, lake, forest, and aquatic ecosystem. The message is simple: different ecosystem, one common pathway. We attain spectral signature. With this spectral signature, we combine biophysical variables in order to obtain spatial information. And then using this kind of product, we can apply environmental intelligence. The different ecosystem, one common language, spectral signature. From spectral signature to territory, turning light into environmental knowledge. Well, that's it. Thank you. Thank you very much.
Moi, j'avais une question.
Oui.
Vous avez montré différentes cartes de concentration spatiale au
Yes.
niveau des lacs. Et donc, on voit que c'est une technique très puissante de mesure. Et ma question, elle est de l'ordre de la qualité de l'eau.
Por la fleuve o por le lac?
Au niveau des lacs.
Ok.
Et donc, selon vous, quels seraient les éléments nécessaires pour transformer ce type de suivi satellitaire en un système opérationnel d'alerte pour la qualité de l'eau dans les lacs?
I think the most important when you start to create this kind of monitoring system is to implement or to select the best atmospheric correction. For example, today there is a lot of methods to atmospheric correction for continental waters. For example, Aquatic or Ecor or another are very specific to mitigate the effect of the sampling. If you don't avoid this kind of specular effect, it will not possible to find a good correlation to to obtain a robust retrieval model. The other is, for example, in lakes, we have the problem the water agency always collect information in the shoreline, but there is no in situ data in the pelagic zone. It's very important collect specific data in the whole lake. For example, in the middle of the lake or some parts, it's very difficult to collect information because it's very rare. It's very important for the representative to, to, to collect information in the whole lab in order to estimate with a good precision this synoptic map. And the other, I think the most important to obtain a good resource is try to program the path of the satellite at the same time to go to the fieldwork. And you try to wait to the time of the pass of the satellite in order to collect the water sample. It's very important. I saw in the last project that is a good strategy to have a good correlation.
Un grand merci à Santiago YEPEZ pour votre présentation très claire, très
Merci.
intéressante. Donc, merci à tous et je vous souhaite une très bonne journée.